Good day to our respected lecturer, Dr. Jack. Today, our team Group 3 from FDMJ is to present our operating system group project. Our project focuses on a critical infrastructure development, which we have designed as the Phantom Lake Protocol Schedule Quarantine Zone implementation. Using Oracle Feature Spot Manager running a robust Debian 11 Linux distribution, our ultimate objective was to design, configure, and regularly validate a hardened, isolated multi-service environment capable of maintaining total data integrity and strict network control.
Hello, Dr. Jack and peers. I will be demonstrating network configuration setup for the Phantom Lead Protocol project. Let's jump straight into our virtual environment settings. Looking at our Debian server, network adapter 1 is explicitly attached to NAT interface. This handles external routing to the server, can access the internet to pull down service repositories. Next, let's look at the Debian client virtual machine configuration. This network adapter 1 is enabled and attached to the internet network using the identifier net internet. This sets our secure isolated zone. Returning briefly to our Debian server settings, we can confirm that network adapter 2 is enabled and linked to the exact same internal network name in NAT. Both virtual machines share this matching name, establishing our secure private network segment. Now let's verify our routing rules directly inside the server terminal. I will run ping 8888 to test outbound connectivity. As shown by the active sequence of echo requests, our server communicates properly with the external web through its NAT adapter. To confirm the server's target configuration, I will run IP8 show info. The output demonstrates that our internal host interface is statically configured as the gateway address 192.168.1.254/24, providing our secure backbone. Moving to our client console terminal, let's view its interface configuration by running IP8. The output clearly shows that the client has been assigned the IP address 192.168.1.5. This validates that our team's DHCP is listening on the correct interface and actively serving our .5 to .10 boundary. I will test communication across our private virtual sector by running ping 192.168. Next, I will test communication across our private virtual sector by running ping 192.168.1.254 to target our server gateway. The packet transmits successfully with zero losses, confirming a functional internal link between the host and client. Finally, let's verify our isolation constraint by running ping 8888 on the client. Notice that the terminal drops all subsequent packets and freezes completely. This freeze represents a network is unreachable state, meaning our security rules are completely working, leaving the client cleanly isolated in our quarantine zone with no outside internet access. Everything functions perfectly according to our protocol instructions. Thank you, everyone.
Morning everyone, my name is Chee, and today I'm going to present my DHCP service in my operating system mini project. So first of all is the configuration of DHCP service. So as you can see, I have already downloaded the DHCP server and it is active, which means it is running. And I already changed the interface before to ENP0S8, which means ETH2. And I have already set the range of DHCP from 192.168.1.5 to 192.168.1.10. Now let's test from the client side. So first of all, we will request an IP address from the server. Now the IP address is requested, and now we're going to check the IP address. As you can see, our IP address is 192.168.1.5, which is in the range. Now we're going to ping the server to check its connection. As you can see, there is no packet loss, which means we have a connectivity with the server. Now we're going to ping to 8.8.8.5 to check the connectivity to the internet. As you can see, there's a 100% packet loss, which means we have no connect to the internet. And that's all from me. Thank you.
Good day everyone, I'm ZHEE and I'm responsible for implementing the SFTP for our project. In the configuration, we need to type tpkg-l grep open ssh-server. This is because before configuring SFTP, the administration need to verify whether the open ssh server daemon is actually installed on the system. So after typing the command, the system print a line showing that the open ssh server package is installed and configured. Next, the terminal open the sh conference text file in the GNU Nano editor. Near the bottom of the file, add the following isolation and protocol rules. Listen only on internal network interface, enable SFTP subsystem. After that, press Ctrl O to save, press Enter, and press Ctrl X to exit the Nano editor. After exiting the editor, the next step is user identity verification. Type ID researcher to check if the specific user account designed for SFTP files transfer exists and to find out what user ID, primary group, and supplementary group are typed to it. After finish this, we will switch to the client machine to testing the connection. It should be performed to verify the secure file transfer protocol environment works seamlessly. In client machine, first we type SFTP Researcher Alliance 192.168.1.254. This command initializes a secure file transfer protocol connection to the SFTP server acting as the designer user. After that, it will show connected to 192.168.1.254. Next, when type pwd, this ensures the connection places the user in the correct initial directory location before attempting any file upload or download. When type ls, it will show a list of existing files inside the remote directory. Next, test uploading a file from the client to the server, so type put text.txt. It will show the files is transmitted and have the path and progress. Next, to download a file, type get test.txt. The file is fresh and test download permission by grabbing a file from the remote system and transferring it to the local system directory. Lastly, type exit to return back to the normal client's terminal prompt.
Okay, hi, I'm Chloe. So the first step is I will verify that Apache 2 is installed on the server by running this command. This command checks the list of all installed packages and filter for Apache 2. As you can see, Apache 2 is listed here, which confirm is successfully installed on this server. Step 2, I will open the Apache 2 port configuration file to show that the listen directive is having changed to bind only the internal network IP address. As you can see this file, the listen directive is set to 192.168.1.254 equal 18. This means Apache 2 will only accept connected on port 18 from the internal network interface ETH2. It will not listen on 0.0.0, which means the web server cannot be accessed from the internet. Right now, I will press Ctrl X to exit Nano. And step 3, I will verify the virtual host configuration to confirm it also bound to the correct IP address. I will write this command. This command search all files inside the site available folder for the virtual host directive. The output shows virtual host 192.169.11254 equal active, which confirm the virtual host is correct configured to only serve requests coming from the internal network at this IP address. And next, finally, I switch to the client to test that the web server is accessible from the internal network. I write this command, curve HTTP, and I'm running the curve from the client to send an HTTP request to the server at this IP address. As you can see, the HTML content of the internal pointer page is returned successfully. This confirms the Apache 2 web server is running correctly and accessible from internal network clients. This complete and right now you can see I opened the Fox. You can see the Apache 2. This is how they look like, the website look like. Okay, now this complete the demonstration of the web service. Apache 2 is installed, bound exclusively to 192.168.1.254 equal 18, and successfully serving content to the internal network client. That's all. Thank you.
Good morning everyone, my name is NARENTHIRAN, son of MURUKAN. Now let's pivot to the implementation details of our database server module. To prove our database management instance is properly packaged and registered within our server environment, I am executing gpkgl group MariaDB _ server. The console output confirms that the MariaDB package is safely installed and ready on our core system architecture. A core security objective of this protocol is strict endpoint binding. I will recursively grep for our socket definitions inside the etc MySQL configuration directories. As displayed, our system is explicitly configured with byte address 192.168.1254. This locks down the database instance, ensuring it only responds to incoming queries from our internal interface, making it completely invisible to outside networks. Now let's interface directly with our secure database runtime engine by accessing the monitor terminal using administrative privileges. Once authenticated inside the MariaDB, I will verify the presence of our specific project storage scheme by running a query for our target database name. This engine returns our database phantom. Next, we map our tables by executing a structural lookup for our required dataset. As validated by the terminal output matrix, our core data table sensitive_data is initialized and intact. To check our security access control, let's query our system privileges table for our operational user accounts. Note carefully that our account labeled internet user is restricted to the host wildcard mask 192.168.1.%. This configuration limits authentication exclusively to nodes connecting from within our internal subnet range, blocking any local server access or external internet exploit. Let's shift back over to our clean client machine terminal. I am executing a socket scanner by sudo sstenlp grep 3306. The command returns absolutely no output on the client terminal. This is functionally brilliant and expected. It proves that the port 3306 is not open or listening on the client machine itself, ensuring a hardened and clean quarantine zone. To interface with our records, the client must establish secure path across our virtual link. I will initiate a connection by typing MySQL page 192.168.1.254 internal user P. Upon executing and inputting our secure credential, our client successfully negotiates access across the interface network and drops directly into the active MariaDB instance running on our server terminal. To finalize our operation, I will select our active project structure by using the command use phantom leak. Then I will put our secure document assets by issuing a standard data dump query, select all from sensitive data. As you can see, our target records, including our encrypted repository files and corresponding system timestamp, transfer over the securely and populate directly onto our client console screen. And finally, we exit our secure database console line smoothly. Every single element of our operational matrix or network interface binding to secure storage containment functions flawlessly under the Phantom Leak project specifications. Thank you very much, Dr. Zek.
To summarize, our team has successfully engineered a circuit automate internal network environment by developing 3 code pillars. First is network automation. We implemented a DHCP server that dynamically allocates stable network configuration to internal clients. Next is hardener file transfer. We configured an isolated SFTP service binding it exclusively to our private IP 192.168.1.254 to eliminate external network attack. Last one is web infrastructure. We host an internal web server to reliably deliver application and service across our local subnetwork. Every service was strictly validated through empirical testing, including checking socket statistics, verified IP addresses, and completing error-free file output and download, we have proved that our infrastructure is cohesive, fully functional, and securely isolated.